Good morning. I'm Arshad Ahmed from Savita Engineering College, a final year student. My project is LLM powered intelligent appliance energy simulator and advisor agenda. In this presentation, I will first introduce the project and explain the motivation behind it. Then I will discuss the problem statement and the scope of the project. After that, I will explain the methodology, system architecture, and UML diagram. Then I will cover algorithm, implementation, details, outputs, and test cases. Finally, I will conclude the presentation with results, future work, and reference. Introduction. In most households, energy bills show only a final total amount. They do not show how much energy is consumed by individual appliances like AC, fridge, or washing machine, or oven, etc. But because of this, users are unable to identify which appliance is consuming more power and where energy is being wasted. As a result, energy saving decisions are mostly based on guessing. Our project addresses this issue by providing an appliance level energy simulator. It uses deterministic energy formula for accurate and combines them with LLM based intelligence for realistic usage predictions. Additionally, users can interact with the system using natural language and explore what if scenarios where energy makes which makes energy planning much easier and practical. Statement of the problem. Existing energy solutions either show only aggressive data or require expensive hardware like IoT sensors. Even when recommendations are provided, they often generic and technical, which normal users find difficult to understand. Another major issue is that users uh, cannot test hypothetical changes. For example, they cannot easily check whether what happens if AC usage is reduced by 1 hour. So hence, there is a clear need for hardware-free, explainable, interactive energy advisor system like us. So it fulfills that gap. Then, scope of the project. This project entirely on software-based solutions. We use a curated data set of estimate of approximately 180 real-world appliances categorized into 15 groups. The system performs appliance-level energy simulation using usage patterns, seasonal factors, and behavioral multipliers. And AI-powered advisor layer generates personalized suggestions for each and every user, and explore also helps in exploring what if scenarios through a web-based interface. Out of scope. This phase of project does not include real-time monitoring or hardware integration. We are not directly integrating electric board bills system or live tariff APIs, and renewable energy sources like solar panels and battery optimizations are also excluded. Then commercial development and long-term AI learning are planned only as future enhancements. Then methodology. In first stage, we create a structured appliance data set that contains technical data like voltage and usage patterns. In second stage, user configure their household appliances and provide contextual information such as family size, season, and etc. In third stage, the system predicts realistic daily usage hours using a hybrid approach that combines AI interface and rule-based heuristics. In fourth stage, a deterministic simulation engine calculates energy consumption at both appliance and household level. Then in the fifth stage, the system compares simulated consumption with user-defined energy targets and identify area of excess usage. Then in the sixth stage, the LLM converts numerical optimization results into simple human understandable recommendations. Then in the seventh stage, uh, uh, users are allowed to interact with what if scenario to explore hypothetical situations using natural language queries. Then in the final stage, in the eighth stage, all modules are integrated into a single web page application and tested for accuracy, reliability, and user experience. The architectural diagram. This diagram shows how the entire system is structured. User inputs uh, are processed by a usage prediction engine and passed to simulation core. Uh, the optimization engine analyzes the result and send them to LLM advisory layer. Then a centralized data foundation support consistent data access and ensures reliable calculation access across all components. And then data flow diagram. In this diagram explains the high level data flow in the system. User appliance details and weather context data are given as inputs. The intelligent energy simulator processes this data and returns simulated energy result and optimize recommendations back to the user. Uh, it's a detailed one. This diagram shows a more detailed internal data flow, appliance configuration, usage prediction, simulation optimization, and what if analysis are executed step by step. Then each module processes a structured data, ensuring transparency and traceability in calculations, which provides more trusted and seamless performance and experience with the user, and also does not compromise in the privacy or anything else. Then UML diagram use case. Um, the use case which represents system functionality from user's perspective. The main actors are user, the external LLM service, and the admin. User or configured appliances run simulation, set target, and explore what if scenarios. Then the LLM provides intelligent reasoning, and admin maintains data set and system health. This diagram visually shows all user interaction inside the system boundary. Each oval represents a system function. This ensures that all functional requirements are clearly captured before uh, implementation begins. Then the class diagram. This slide explains the class diagram, which shows the static data of the system. It defines classes, their attributes, and relationships. This helps in organizing data logically and ensures a modular system design. This user class represents household users. The appliance the appliance class stores technical details like power, rating, and efficiency. The user appliance links user and appliance with usage information, prediction, simulation, and simulation result handle the usage estimation and energy uh, calculation. Then optimization plan stores energy saving strategies, and LLM advisor generates human readable advices. Then sequence diagram. This diagram explains step-by-step uh, execution flow. User requests move from the front end to API key, then uh, to simulation and optimization engine. Finally, the LLM processes the result and send recommendations back to the user interface. This diagram also includes what if scenarios. Instead of recalculating everything, the system intelligently adjusts response using AI. This improves performance and provides faster feedbacks. Then algorithms used in this project. Energy consumption is calculated using standard electrical formulas. Usage predictions combines AI-based interface and heuristic fallback method. Then optimization algorithm identify high consumption appliances and possess reduction strategies. Then the LLM converts numeric results into personalized advices. Then the hardware requirements for the system. The system is designed to run on commonly available hardware, and Intel i3 processor with the 4 gigabytes of RAM is sufficient uh, to run this project. Then software requirements. The application supports Windows and Linux operating system as well. React is used for front-end development, while Fast API with Python is for used for backend services. Data is stored using lightweight formats like JSON and SQLite. AI services are integrated using APIs. Then system implementation. Uh, this slide summarizes all modules, including dataset management, um, prediction engine, simulation engine, optimization engine, AI advisor level, and UI integration. Then technology stack and integrations. All modules communicate through REST API. Structured prompting ensures reliable AI output. Feedback mechanisms ensures system stability even if AI services are unavailable. These slides highlight key backend and front-end code snippets. They demonstrate AI initialization. They demonstrate AI initialization and energy calculation logic, optimization logic, API routing, and front-end front-end state handling, etc. Now let's run the simulation in two. tabs. One is for front end and the server. Then we have to click localhost slash. Okay, and here is the home page in which we have device configured, and it's the first view. And here we have to configure the device, and we can simulate. And these are the three parameters in which device configured, and estimated monthly consumption, and target versus evaluated. Now let's add a device. So here we have to enter the desired monthly units. So based on this, the recommendations will be given if the desired monthly units is low or less. So click on add device. So we have to add. Here is the list of main categories in which we have subcategories when we choose that. So here we can see in the appliance, we got some subcategories. So here is the variance whether we have to, so we can choose that. And is the rated power and the number of quantities that you have. And you can also give some notes, but then you have to click add. Then here is the usage R predicts. It also predicts, but the usage R that is given is be more accurate. So let's give it. So let's fast forward. Here I have given some list of devices. So washing machine one and etc. So let's go to the simulation in which it shows the number of devices that you have added, and the here is the monthly consumption of the devices that you have selected, and it is the target, that is difference gap. So it subtracts the monthly consumption from the current one. So and here you can also see the highest uh, energy consumption by the bar that is shown here. And once you click run optimization, then it gives you the optimizations where what you can reduce, you can replace, but it shows how much energy can be saved. Then it also shows the detailed breakdown of what each devices is using per month, and the highest is shown and the obviously the upwards. In the energy story, it shows what to reduce. Then, if you're not satisfied with that, then we can go to the what if couch, and in which you can type like what if I use AC and for an hour. Then it gives instant responses. So we used an API for this. These slides showcase system output such as dashboard, device configuration page, and simulation, and energy breakdown, detailed energy breakdown, then optimized recommendations, and what if scenarios, what if interface, then what if chatbot UI, then test cases. These test cases verify correct functionalities of device configuration and input validation, AI-based usage prediction, then energy simulation and calculations, and intelligent optimization and recommendation, what if scenarios, and etc. Then the result. The system achieved high accuracy in energy simulation. It, it identify potential energy saving of up to 30%. User engagement through interactive what if analysis was also very high, as we can infer. Then, in conclusion of this project successfully demonstrate a hardware-free, intelligent energy advisory system. It combines accurate simulation with AI reasoning to provide clear and actionable insights. Then the future work. In future, we are planning to integrate real-time data, smart pricing model, renewable energy awareness, and advanced AI personalization, so that it can be even more. It can provide even more uh, uh, customized and personalized recommendations for everyone. These slides list the research papers and journals referred during the project development. Thank you.